mathematics. How much gold can you hold in an elephant's ear? When it's noon on the moon, then what time is it here? If you could count for a year, would you get to infinity or somewhere in that vicinity? When you choose how much postage to use, when you know what's the chance it will snow, when you bet and you end up in debt. Oh, try as you may, you just can't get away from mathematics.
All right, grade 12s, welcome to probably your final official calculus class where you will get new information. And we're going to do our last application today. It's called the volumes of revolution. Now, to do this, we're going to go fast. We're going to skip over some things. I'm not saying skip, but I'm going to explain them quickly and maybe not in as full detail as maybe some of you might like, but that's okay. In the end, there is a formula that we're going to follow when we're taking it. So the theory behind it is important, and I'm going to explain it. You may or may not understand the theory behind it. Hopefully you do, but if not, that's not the end of the world. As I said, there is a formula that we're going to get to. And as you continue to do more and more calculus in the years to come, this is one of those topics that will make more and more sense as you go along. Now, in order to do this, we're going to draw along on some information that you would have gotten in a physics class in the past, maybe. At some point, you were finding areas under curves using a method where you would find a whole bunch of rectangles and triangles, and particularly rectangles, and you would find the areas of rectangles, and then you would add them up, and then you would hope to get something close to the area under the curve, right? And we didn't like that method because integrating is a much better way of doing that. Integrating, what it does is it takes all those slices, an infinite number of slices of rectangles, and adds them all together in one integral formula. So with volumes, it's similar. With volumes, what we're looking at is we're taking a rectangle, okay? And we'll do it with an example over there in a minute. And we're taking a rectangle like this, where the height is y, or f of x, right? It's the y value is defined by the function, so it's f of x or y. The width we call is delta x. It's just a change in x along the x-axis here. And we're going to take this and we're going to rotate it around the x-axis. So we're going to say we're going to take this and we're going to give it a little rotation. And what that would do is it would give us this picture. Now this is my attempt at a three-dimensional picture, but what you get is a cylinder, right? A very short cylinder. The height of the cylinder is going to be delta x. The radius of your cylinder is going to be y. All right? And so just imagine this coming out of the board, rotating around, going back in. We get a cylinder. I might call this a disc or a puck because its height is so short. But we get this three-dimensional shape that is a cylinder at heart. And we know that the volume of a cylinder is pi r squared h. So in terms of this disk, we have pi y squared, because y is the radius of our cylinder, times delta x. All right, so that's what we're doing. And now what we're going to do is we're going to take this bit of information and we're going to take it to a graph where we're going to have an infinite number of these disks that we can draw at whatever varying sizes if need be, and integrating is going to add them all together. So let's go look at an example on the other board, a generic example, and then we'll get to a specific example when we come back. All right, let's go take a look at it. Okay, so here in this example, what I've got is I've got this black line here as my function. It's kind of a parabola opening up. I didn't quite draw it perfectly, but it's kind of a parabola. Okay, we're going to take and we're going to draw this disk here. Now it's the same disk, the same rectangle that we had on the other board on that graph. Okay, and again, its volume was pi y squared delta x. Okay, we're going to take and we're going to rotate that around. Now what this would give us is, again, this would give us a three-dimensional shape, right? That would look something, right? If we drew it as a three-dimensional shape, it'd be this horn kind of idea, right? Where we get this, and again, here now is the disk that we had over there, okay? Where again, its volume is pi y squared delta x. All right. Now, integrating this formula, we'll find the volume of this shape, because now we're taking the area of this disk times its height, and by integrating it, it's expanding it in both directions. Well, where we'd start at one end and go to the other end, and we would get, it's called a Riemann sum, if you must know, and you can look up Riemann sums, but integrating is a way of taking the sums and collapsing it into one equation. And so the equation that we want to use when we're finding volumes of revolution is this formula right here. Okay, it's the integral of our volume formula. Now, pi is a constant, so I pulled the pi out front, and we're integrating from A to B, so depending on where our lines are, if this was A, and this endpoint here was B, that's where we'd be integrating from, okay? And then it's of f of x, which is y, squared dx, dx being this change in x that we're looking at in here. All right, so this becomes the formula for finding the volume of a shape. Now, the shape, the f of x, is our function, and it can be anything at all, right? It could be a simple parabola, it could be a much more complex shape, it could be trigonometry things. And again, so we're going to be squaring it, we're going to simplify it, and then we will integrate it, and then using our fundamental theorem of calculus, putting in a and b, and getting a volume. And let's go do a practical example on the other board, and hopefully this will start making sense, and then you'll get a short assignment on this. So here's our example. We have find the volume of the solid that is generated when the region under y equals x cubed from x equals 1 to 2 is rotated about the x-axis. All right, so you don't have to draw these out if you kind of get what's going on, but it's a good idea to sometimes give a quick sketch, and some questions will require you to draw a quick sketch. But we should all know what y equals x cubed looks like, so we're just draw a very quick diagram. And I'm going to expand it so that x equals 1 and 2 are kind of far out. So we're going to go like this, and we're going to come like this, and like this, where x equals 1 and 2 are out here. All right, so there's our graph. Of course, we don't need anything that's over here, but it's just there as part of the graph, because what we're looking at is this area here. Okay, so we're taking this area that is under the curve, and we are rotating it about the x-axis. So when we rotate that about the x-axis, what's going to happen is we're going to get, I'm going to just do this with dashed lines, come down here, and we're going to get something that gives us a three-dimensional shape that looks something like that. All right, and we are finding the volume of that three-dimensional shape. So it's maybe part of a funnel or something that might be looking like a funnel. And we'll start with that. All right, so again, now the volume, our function is y equals x cubed, and we're doing that from x equals 1 to 2. So when we go volume equals, it's the same formula, pi r squared h, but we're integrating it. So we're putting the pi out front, we're integrating from 1 to 2. And our f of x is x cubed squared dx. And this is what we have to integrate now. So it's not so bad, because we're going to go volume equals pi. We'll simplify first. We're still going 1 to 2, but now it's x to the 6th dx, which means that this equals pi times x to the 7th over 7, using our basic integration rule where we add 1 and divide by that number, still going from 1 to 2. And so our volume then will equal pi, and we'll pull the pi out front. We're going to have 2 to the 7th over 7 minus 1 to the 7th over 7. And that will give us an answer of 127 over 7 pi. And if you feel like putting that into a decimal, you certainly can. All right, We will do one more example that involves trigonometry on the other board, and then you will get a short assignment. So here's our last example, and this is a bit of a tricky example. Harder than most of the questions you will get, harder than probably all the questions you will get as we end off this unit and end off this course, but certainly something that you could get as you go on into university. What makes this question difficult is that it does require you to remember some of your trig identities from pre-calculus. And that will be something going forward as you move into university, is those trig identities, you still have to remember them. Typically they will be on formula sheets, but sometimes they're not, and they will have to be known. And so here we go. The question is, find the volume of the solid that is generated when the region between y equals sine x and y equals cos x from 0 to pi over 4 is rotated about the x-axis. So again, this is similar to doing a question where we found the area between curves. We are just now doing that again, but now we're doing volumes. We're going to have to subtract one volume from the other. So again, we're going to start by graphing it. And I'll just do a small graph here. And again, y equals cos x goes like this. Y equals sine x goes like this. And we're only concerned with this part here that is between 0 and pi over 4. All right, so again, this point here is at pi over 4. Okay, so now when we rotate that around the x-axis, what's going to happen is this is going to get reflected down here, and we're going to get a funky three-dimensional shape that is, I don't know what you would even call it, but it's a shape that has this piece here and this piece here, and it's a circle on top, and it looks kind of like that. I don't even know, it might be a vase of some kind, or some dish to hold something in, or who knows what it might be. It could be anything, but it's a weird shape. And it's a shape that we would normally have a hard time finding the volume for. I'm just going to erase this so that we don't need it, so that we have more room in order to do what we want to do. All right, so what we have to recognize though is that we're going to be taking the volume of the cosine graph minus the volume of the sine graph, right? Because we want to, again, if we just did the volume of the sine graph, that would be finding us the volume under the sine graph rotated around the x-axis, and that's the part we don't want. We want to subtract that from the volume of the cosine graph. So when we're looking at volume, it's going to be pi 0 to pi over 4 of cos. Remember that cos x squared can be written as cos squared x. And then we're going to go minus pi integral from 0 to pi over 4 of sine squared x. And of course, I've forgotten my dx's. There they are. All right. Now we can bring this together because the constant is the same and the limits of integration are the same. We can bring this into one statement. We can make this pi from 0 to pi over 4 of cos squared x minus sine squared x dx. Okay, now this is where you have to remember a little bit of your pre-calculus. We don't have integration rules for cos squared x and sine squared x, but if we remember from pre-calculus, one of our trig identities was that cos squared x minus sine squared x actually equals to cos 2x. Okay, and now we can find the integral of that. We have an integration rule. The integral of cos 2x is, I'll just use square brackets here, it is sine 2x over 2. And of course we're doing that from 0 to pi over 4. All right, and of course now we'll simplify this. So I'll try to fit it on the bottom here. We'll go pi over 2. We're going to pull out that 2 out front because it's again a constant. And what this is going to give us then is it's going to give us the sine of 2 times pi over 4. I'm going to write this differently so it's easier to see. Okay, sine of 2 times pi over 4, which when you simplify this becomes the sine of pi over 2 minus the sine of 2 times 0, which again becomes the sine of 0. So you've got pi over 2 times the sine of pi over 2 minus the sine of 0. The sine of pi over 2 is 1. The sine of 0 is 0. And so what we've got here is inside the square brackets here, we've got 1 minus 0, which is 1, times pi over 2. And so the area equals, the volume equals 2 pi over 2. Okay, but the trick in this question again is we know how to integrate. Once we have it down to here, we should be able to integrate cos 2x again. You can certainly use substitution rule to do that, or you can just remember that cos 2x is sine 2x over 2. But again, we're using substitution rule to get that. But the trick here is remembering pre-calculus trig identities. Cos squared minus sine squared is cos 2x. And of course, we started it off by remembering or looking at the graph and recognizing that in order to find this volume, we had to do cosine minus sine, and that's how we started. All right, I hope that makes sense. You're going to get a short assignment that will have some fairly basic ones. May throw in one that's maybe slightly harder, but that will be the end of our course. In terms of new content, we want to spend a couple of days reviewing, and then we'll have our final test. All right, look for your assignment on Connect. It'll be a handout, and we will see you soon.